Um, my name is Carl Ewald. I'm one of the instructors at Cabrillo teaching engineering. I teach the materials engineering course, the strength of materials course, the dynamics course, the computer applications for engineers course, the engineering communications course, and I often guest star in this class a little bit. We like to give you exposure to all of the different instructors that are teaching. Well, maybe not all of them, but a lot of the instructors that are teaching. And I'm going to start with an exercise I do it in all of my classes, which is a mindfulness process. If you've ever played like a Mario video game, like a side scroller or a platform game, oftentimes you kind of end up having to jump over some lava, land on a little platform, and then you can take a breather because nothing's trying to attack you right then, and then you can make your jump. So the idea here is that your neurochemistry, which is really, really important to our capacity to think and to reason and to do stuff. And it often is challenged by all of the things reaching out to get our attention. We're going to do a little mindful exercise, which is to just center your attention, take your entire attention and try to focus it on some sort of body sensation. So the most typical one that people use is that you're going to just take a really big deep breath. You're going to release it and just try to let the tension go from your body. And then you just want to focus your attention, like all of your attention on something like trying to just feel the sensations of the air going through your sinuses, through the back of your throat, into your lungs, maybe your belly. And the idea is that by doing this, you can calm and kind of seize control of your neurochemistry. And then just like jumping to that little platform, then we can jump beyond that to a task, and our task will be Engineering 5 today. So like I said, you'll see athletes doing this before like key performances. If you ever watch like ski jumpers, they always take this moment of like silence, or maybe they're listening to music, but the idea is they're not letting their future evaluation in their head take over. They're like, they want to be in the moment because their performance in the moment is really what matters. And that's really important for engineers and for everyone, really. So I know that's a long intro into this, but just go ahead and take a moment, take a deep breath. Feel the sensations as the breath is taken inward, and then release it, and just focus your attention on those sensations. And if your mind runs away from them, just try to bring it back. So take one more deep breath. Hold it in, release it, and we'll get started. All right. So today we're going to focus on a bit of my, a piece of my history. So I grew up, I was like a high school student. I went to high school in 1982. So it was right at that period of the 8-bit video games. And I was really into this idea of games, really, video games. I mean, it wasn't like a super sophisticated thing. It was just like, I liked games. But I didn't have a lot of money to buy those games. Ironically, like those games, even back then, were almost as expensive. And if you account for inflation, they were probably more expensive than games now. But I ended up buying a computer. I could buy a really simple basic computer for about $250. And I started to write video games. And so as I went through high school and played with the computer, I was kind of over it when I went to college, or at least I thought I was. But those skills, the programming skills, came back to help me as I was studying first aeronautical engineering, then mechanical engineering and material science and engineering. And all of my graduate work as a master's student and as a PhD student were writing computer models to try to simulate the behavior of these material systems. And the idea there is I was running these machines that could basically lay down these really, really, really thin layers, like on the order of, hundreds of atoms thick. And it would take like a week to make one of these samples. And then you would process it. And if it didn't work, then you'd try again. So even back then, if your computer could give you insight into what was happening, you could write a computer model and you could avoid doing a whole week's work to not get what you wanted. And you could start to use the computer to help you get what you want. It was well worth the investment. So you'll see that now we don't see a lot of like failures and things. And that's because our computer modeling has gotten so good that we don't tend to see the kinds of catastrophic failures that we saw, say, in the early space industry, where it was like, put the thing on the launch pad, set it off and see what happens. And there is still some of that. You'll still see some spectacular failures as, say, SpaceX is trying new rockets, trying new, like whole new approaches, actually. I don't know if anyone's seen their Starship, those recent launches, where it's like this big fat thing. It looks like a grain silo and it comes down and kind of floats down. And at the very end, it swoops around and tries to land. And they've had quite a few failures, but they also had one that landed the other day. So in any case, that whole era where computation, like computers and the ability to kind of run these programs to predict the future, to control things, is going to be really prevalent in your period of time of being engineers. And so we want to give you a little bit of introduction to those fields, the computer field, because when you talk about robotics, you talk about mechatronics, you talk about almost anything now has an embedded computer in it. And you may not be the one programming it, but you may want it to help you out as you tackle different tasks. So what I'm going to do is first take a look at these slides, and I'm assuming that you can see them. So let me present it. Can you give me a thumbs up if you can see these? All right, cool. So these slides cover both electrical engineering, a little bit of computer engineering, and kind of the survey that we've been giving you along the way of just different fields, how they fit together, and some of the different aspects of them. So electrical engineering is really, really common. You can see that it employs the largest number of engineers, and it can be at the scale of like the giant big power plants and the distribution of energy throughout the world through electrical wires and transmission infrastructure, or the tiniest little embedded chip memory, these little, I had it nearby, but I think I've misplaced it. But you have these tiny little chips now that hold gigabytes of information. Like as my 10-year-old self playing with computers, that was unimaginable. But now the kind of sci-fi life is here. Um, so, it can be communications, it can be power generation. Electric vehicles are another big giant thing that we're moving towards. You've seen Tesla take off, but almost every car company now is building electric vehicles. And a lot of them already have plans for when they're going to stop building non-electric vehicles. That's already in their kind of 20 and 30-year plans. So electrical engineering is vast. There's a lot of opportunities. There's a lot of different industries that employ them. Go to the next one. So here's, whoops, it's catching up with all my clicks. Okay. So here's kind of just a series of applications. So, vehicle control systems, which, that can be things like the heating and cooling, but also now we see self-driving vehicles or, kind of, what do they call it? Like autopilot type of systems that, will not just keep the speed the same, but will follow a lane. And you're going to continue to see that advance. We have the satellite communications, which we take advantage of all the time, cellular communications, power plants, circuit boards, appliances. It's hard to imagine a world without refrigeration until the power goes out for a week. And then you're like, wow, I used to like ice. Ice was amazing. Turns out in the, 200 years ago, there was a giant trade that was just people would take their ships, go up to the north, saw ice out of the saw ice blocks and put them in the boat and go down into the warmer climates and sell that ice, because that was the only way humans knew how to get ice, is when the environment made it for them. They didn't have refrigeration. Like, all of those are inventions that engineers and electrical engineers participated in. TVs, DVDs, media, all that kind of stuff, music, medical instruments. There's a lot of electrical engineering involved in medical instrumentation, recording equipment, music equipment, synthesizers, amplifiers, all of that kind of world, lighting shows, whether it's just kind of the mundane light of, just having a fixture up here that gives me light. So when it's dark outside, I can make a choice of what I do. In the developing world, there are a whole bunch of projects, for example, that they'll take a weight and they'll have a little generator and an LED bulb, and you just pull that weight up like an old grandfather clock. It slowly comes down from the ceiling, and while it's coming down, it's generating enough electricity to light that light, so that students in villages that don't have electricity have an extra couple of hours where they can decide, oh, I can work on my homework now because there's light, and it doesn't have to come from a flame. Networking hardware, you're constantly seeing the evolution of networks. The 5G thing that is advertised for all these phones, the new iPhones that have 5G, that's the 5th generation of kind of major networking hardware. And that enables a lot of things like high definition video. If there are some gamers, there are now services where you don't even have to have an Xbox. There's an Xbox in some server room somewhere in somewhere else, and all you are is a remote network connection to that. And it's gotten to the point where the networks are so quick and so the quality of service is so high that by the time you click a button in your house, it's gone all the way to some server in, say, San Jose or farther. Click the button there, made a response, and it sends you back video so quick that you can't even notice that that's transpired. There's firmware in all sorts of things, like even this calculator, right? This calculator has a little computer built into it. And so there's people that spend all their time writing very specialized programs for very specialized devices. Aviation controls. If you've followed the Boeing 737 MAX, right, that was a grounded airplane. The problem with that airplane is that the software essentially was sort of operating without the knowledge of the pilots, and it was saying, no, 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 you're trying to crash the plane. And the pilot's like, no, 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 you're trying to crash the plane. And in that interaction, the plane crashed. But that, all of that, you know, the human and kind of machine interaction is often negotiated through software. And a lot of that has to do with electrical and software engineers kind of collaborating. And then, of course, we're seeing the era where everything has a tag on it, a GPS tag. So if I want to know where my cell phone is, I can log in and find it, see it on a map. And I find out it's just in the other room. I didn't leave it at the restaurant. But you know, they have all of these little tags that you can put on your keys and different things to find stuff. And that's all kind of being built into the infrastructure. Let me stop there and just ask if there are any questions. Does anybody have any questions? You can put them into the chat, and you don't have to stay on topic. I'm not a big super, oh my gosh, that's an off-topic question. Anything out there? It's okay. Just if you come across them, think about them, then let me know in a bit. Okay, let's move on to the next slide. So computer engineers, they focus more on the electronic parts of like the computer system. So that could be things like, how do I arrange these atoms into little teeny transistors? So has anyone heard of Moore's law? Moore's law was this law that kind of started when semiconduction happened. It was discovered in the 50s, and it basically found that they could make things smaller and smaller, and that the size of transistors would basically become half as big as they were the year before. And it's gotten to the point where now, like a modern Intel processor, they're using these. So how big is an atom? Does anybody know approximately how big an atom is? How many meters?
The nanometer.
Yeah, they're about a nanometer, which is a billionth of a meter. So if you imagine taking atoms and you line them up and they're like 1 meter long, this is 1 meter long is back like probably about this. There's a billion atoms, and they're building transistors now out of, you know, like kind of on the order of like a 9 by 9 by 9 cube of atoms. And they're very specifically placing them so that they will do our computation work. So they're really pushing the limits of like how small you can make a transistor. And the reason that's important is because what we're seeing with like the transition to these phones, like not only is this phone probably millions or billions of times more powerful than the computer I worked with in the 1980s. But it also uses much less energy because it requires less energy when things get smaller, because you're not, you know, it's kind of like if you imagine pushing a really big, old, heavy car like down the road because you ran out of gas, like that takes a lot more effort than if you're pushing a tiny little golf cart. Well, that kind of works in the electrical world as well. So the reason that we have longer battery life, you know, better video, all of those things is because that trade-off of when things get smaller, they require less energy. And then they get into things like machine learning, artificial intelligence, operating systems, computer networks, right? That's more of the, like that, the relationship between electrical engineers, computer engineers, and software engineers. Has anyone paid attention to the new Macintosh computers? The new Apple computers? Let me.
The ones that have their own operating systems.
Well, they have their own operating system, but they also have their own chips now. Has anyone seen that? Let me, I'm just
Actually,
gonna
M1
bail it.
chips.
Yeah, yeah,
Yeah,
let's,
the ARM based, right?
yeah. So we're just gonna take a little visit to their website. And gonna go to their Mac section. And they have this chip that they're advertising, the M1 chip. And let's learn more about the M1 chip. So this chip basically takes things that used to be separate, like the microprocessor, the graphics chips, the RAM, and they basically put it all into one chip. And that's what they call a system on a chip. The whole thing, right? So it's using a 5 nanometer process. So remember, an atom is about a nanometer. So even now, like they're talking about like a 5 by 5 by 5 little cube of atoms is sort of the process in which they can control the size of things. So they're kind of like sketching out the structure, right? So they have the CPU, which is the central processing unit. It's the thing that does all the kind of multi-purpose kind of program. The GPU, the graphical processing unit, which is designed for dealing with all the graphical transformations, the 3D transformations. Those types of calculations are what we call parallel. They're parallelizable. When you study farther, you'll find out about a type of math called linear algebra, and it heavily relies on linear algebra. And these chips, the GPUs, are able to do that kind of processing very, very quickly. It also has this thing they call the neural engine. So that is with modern learning machine learning techniques, there's special kind of chips that are very efficient at doing that kind of work. So image recognition, voice recognition, even self-driving cars are using neural networks to make decisions, not like heavy-handed programming. So, you know, they kind of talk about it and they're really using it as a marketing thing, right? This technology becomes a marketing discussion. They talk about how they have 8 cores for the processor, but some are super efficient. So they run in low power mode. So when your phone, right, it's the same kind of chip architecture that's in an iPhone, is they're making the distinction of I need to do a lot of work really fast, or I just need things to kind of like move along. It doesn't matter if they happen super fast, like super fast in a computer sense is like 3 billion things per second. So, you know, I always laugh that like, why would I buy a new computer so my computer could wait 12 billion things, could have done 12 billion things while I'm waiting to type my name because I'm like the slowest glacial moving thing in the world. And again, this is not because you're going to be tested on any of this. It's just to show like how this all kind of fits together in the evolution of our devices and how those devices then kind of become important. There was no, if you went back 10 years ago, no one was talking about having a special neural engine chip except in the R&D centers of all these companies because they saw it coming. So they started to say, how can we efficiently use this? In any case, I won't spend any more time there. Let's go back and continue presenting from where we were. Hopefully it picks up where we were. It does. So these engineers work at all of these different kinds of things. So if you're looking at even computer or not computer, but like green energy, like solar versus wind versus geothermal, there's tons of effort being spent like trying to develop new battery technology. Uh-oh. So computer engineering, if you like try to disentangle it from electrical and computer and software engineering, is really focused on the hardware part of it, the chip design. So that whole thing that we saw from Apple, that's like a computer engineer is figuring that stuff out. And they're doing this integration where rather than having these systems that, oh, here's my RAM, here's my GPU, here's my CPU, and then they all kind of come together, they're just like, oh, we'll just integrate it all. It'll be much faster if they live right next to each other and I don't have to have wires, connecting them. And then just the kind of how do you do this fabrication? Like, how do you manipulate things in a way that you can build things out of um, atoms at this 5 nanometer scale? Like that, you can imagine must be pretty tricky. And there's a lot of work that goes into that. And then just testing and assurance. How many people have bought like a gaming system that has and bought a chip? And you kind of, there's like different speeds and there's different options when you choose that chip. Has anyone ever done that? Okay. Looks like no, so we'll just skip that over. Just kidding. um, they always try to make the good chips. Like they don't like specifically make better and worse chips. What they do is they make the chips and then they run them at different speeds. And then the ones that start failing at a certain speed, they'll sell as like, oh, this is the lower cost i5 processor because it's not as fast. But it's the same chip. It's just like they didn't redesign it. It's just that some flaws in the manufacturing led it to only work at this speed. So that's a little different. And so they're sorting all of these. So this whole test and quality assurance part of computer um, hardware is really important because it's part of how the economics works. So when they take a wafer and they put a whole bunch of chips on it, and then they cut them up and they find that 10% are the highest quality, super fast ones, they charge more for those. And the rest of them they charge less for because they can't run as fast. Software engineering is focused more on the programming parts of it. So that would be things like machine learning, artificial intelligence, this whole notion of cloud-based computing, right? Where it starts to not matter how much memory your phone has because everything isn't on your phone. It's basically accessible to me all the time because it's in the cloud. Well, the cloud isn't. That's just like some marketing thing they came up with. Where is the cloud really located? It's usually like these giant warehouse-sized buildings, usually near some sort of power generation system. So often they'll put them near like hydroelectric projects out in the middle of nowhere. And it's just a bunch of computers that are being monitored and uh, monitored, repaired, controlled, all of this stuff in the most efficient way possible. Because if Google has all your data stored for all your pictures and all your YouTube stuff and all of that, it's their way of making money on that is selling advertising to you, right? And if they can save 4 cents by upgrading their hardware or using a different system, they will, because it's kind of in a way that the system takes on that efficiency without asking consumers like me to constantly upgrade my stuff. Of course, websites, we know that, web applications, operating systems, you see, Windows is one of the operating systems, Mac OS is an operating system, Android is an operating system. There's actually a bunch of operating systems called Linux. They're Unix-based open source systems. And so there's a wide variety of these operating systems. And then there's, of course, the entertainment software business, whether you want to call that gaming or that kind of hybrid where, some games get to the point where they're almost hard to distinguish between movies. It kind of depends on the gaming style, but there is sort of the blending of that. So that's something that software engineers do. There's lots of employers and this is just certainly not even an exhaustive list. The Silicon Valley, which we're very close to, has all sorts of companies that start and stop, and big, huge companies that you can't imagine how big they are that you've never heard of because they do some tiny little piece of the plumbing of how the network works. But we have companies like Cisco, Sun Microsystems doesn't even really exist anymore. It got absorbed into Oracle, actually. It's funny, I got to fix this slide. Intel, you've heard of, Microsoft, Oracle, IBM, Apple, Google, Yahoo, all of the different wireless providers, Verizon, AT&T, those are like T-Mobile, Sprint. Sprint and T-Mobile just merged recently. There's all the manufacturers of these devices. Does anybody know the name of the company that manufactures most of the iPhones? Yeah, you'd think it'd be Apple, right? But no, Apple contracts with a bunch of other companies to make stuff. So Foxconn, I think, is the one that still makes the majority of their phones. But they're a company that basically can make and does make all sorts of different phones. Global information systems, or like GPS. So like GPS, we know is sort of our ability to locate ourselves, but global information systems and this idea that everything has a location, you'll see more and more of that. I don't know. I've certainly seen where if you enable certain features of your phones, for example, or like you have apps for certain stores, when you go into the stores, they'll send you notifications. And like, coincidentally, I just happen to be standing next to this thing that they're advertising to me, right? And so that whole area of business is expanding. eBay, Amazon, of course, you could be self-employed, and there's all of these startups, startups are an interesting. I've worked at a couple of startups when I was younger. They're super fun. It's like they're small. You basically can't avoid working on things because it's not your job. Well, there's only 6 of us, so it's got to be someone's job. So it could be really fun. You get to try all sorts of things. You have a lot of authority. Usually the money, you take less every month, your salary is less, but then you potentially have this big win if the company IPOs or becomes a public company. So there's a lot of options. This is always and probably will always be a very active area for new engineers. So mechatronics is sort of this fusion. We think of it oftentimes in terms of robotics, of mechanical engineering, electronics, and computing. So for me, like a really good example is, why 20, well, not even 20 years ago, you were probably not born. Some of you, not all of you, of course, but let's say 10 years ago, why didn't we see quadcopters as a very common thing that you would just go into a store and be able to buy? What is it about quadcopters? What happened in the last 10 years that allowed quadcopters to come about, become cheap? Well, it turns out a lot of it has to do with the same thing of why these became cheaper, is that, when your phone, as you probably know, it knows its orientation relative, like it can tell whether it's moving and stuff. It has all of these things called accelerometers. It has magnetometers. It has all of these kind of sensors in it. Well, the reason quadcopters came into commonplace in the last 10 years is because sensors got really cheap, computation got really cheap, and batteries and motors became cheap and more controllable. So this concept that you have 4 propellers, like 2 in front of you and 2 behind you. And imagine you have these little dials in front of you, you have 4 dials. And your goal is just to make sure that each motor is going exactly the right speed so that the thing doesn't flop over this way, or that way, or this way, right? Doesn't dump you. Well, that requires a lot of very precise control between those propellers. And so what happens is the quadcopter's sitting there, and as soon as it detects it's tilting, it's like, oh wait, I got to speed up these motors, and it'll speed those up a little bit. So it looks at every tiny little nuanced movement and decides what to do. And that requires sensors to know what's happening, computation to make a very quick evaluation and choice. And then it needs control. It needs to be able to control a propeller and say, I don't want that propeller turning at 3030 RPMs. I want it at 3040 RPMs. So it's the evolution of all of those systems together that allows like a quadcopter to be cheap and right off the shelf. It's easy to control because you're just kind of saying, go over there. And it's saying, oh, I have to manipulate all the speeds of these little individual pieces to go over there. And I teach a dynamics class, and dynamics is it's part of the mechanical engineering field. But like, so imagine the improbability of like, I just move this straight up and down, right? How many parts of my body are moving? There's like, my wrist is moving, my hand is moving a little bit. Maybe you could think of that as my wrist, my elbow's moving, and my shoulder's moving. Right, so all I'm trying to do is make this move up and down in essentially a straight line. But the way my body is doing is by controlling this joint, my wrist, my elbow, my shoulder. So when you have like these robots or these different systems that are somehow doing that, that is a very sophisticated, complicated problem. Like, how much do I move my elbow? You know, how much do I move my wrist? And if you tried to think it through, you would do what a baby does, which is, you know, because they haven't built that coordination yet. Well, our mechatronic systems have to learn how to build that same kind of coordination. So, you know, there are the sort of consumer-based things, like a quadcopter is kind of consumer-based, but it also has an industry, right? So quadcopters are used in industry to do surveying, to spray crops even. Like there's all sorts of things that there's kind of an industry side of this. So a lot of robots, they started off doing manufacturing. They were in like car plants. So there was all of this effort to like streamline and make manufacturing cheaper and more easily changeable, so that some factory that's making item A one day can make something completely different in day 2 without like having to build a whole new factory. Mining, aviation, robotics, defense, transportation. You know, we're seeing a lot of like these automated transportation systems, security, telecommunications, artificial intelligence, automotive. So there's all of this kind of evolution in these tools. I'm going to show a couple of videos. These are, let me make sure I shared my sound. I think you should be able to hear this. Thanks. So just to try to grasp the sophistication of that movement, look at all of the articulation, all the little tiny movements that robot is going through to make that one kind of jump spin. And so I think the reason I mention this is that is machine learning is essentially it's beyond like the micromanagement of human beings at this point. It's basically like letting the machines build that kind of dexterity of, well, I just want this to go up and down, but going up and down means I'm changing all of these different things simultaneously, and it's figuring out how to do that. And that kind of revolution in computing is underway right now, and will certainly be a part of your experience of the engineering field. I picked another one, which is their little robotic dog. It's named Spot, I think. Yeah, it is. It's named Spot. Animal abuse right here. So in that demonstration, you saw a lot of the little pieces that I was talking about. That robot is just basically being instructed to go through the door. Like in terms of the humans instructing it, it's like go through the door. And then the robot is making all of the decisions of how to actually achieve that goal, right? And every time something gets in the way, they haven't built the frustration engine into the robot yet, so it just like rage quits and lays on the floor in the fetal position and cries. Thankfully, it hasn't gotten to that point, but you can see it's just like, okay, this is my new situation. I have this problem. Someone's pulling me backwards. Okay, let me start over again. And a lot of that, like I said, is part of the machine learning, artificial intelligence part of it. And so it's learning certain patterns. In any case, I just wanted to share those. Like, I think they're cool. I think that we're on a cusp of, I mean, you always say these things like a cusp of a revolution or whatever, but I mean, the capacity of these robotic systems to evaluate their circumstance and make decisions is advancing in a really meaningful way. And you'll see more and more of, I mean, certainly in in the next 10 years, we'll see automobiles that drive around town completely on their own. They don't need a human being involved. And we already have systems that will do that. I think they're just not quite resilient enough for every circumstance. All right, so I think that is the end of these slides. Yep, that's the end of them. So let me stop and just take a minute to ask any questions or get any comments from you.
Well, there's a lot of controversy with autonomous vehicles, especially cars. You know how there's the awareness of if a car goes by itself, whose fault is it going to be if they crash or like I don't know, in that sense. Of course it would be the company, but it would still be a controversial thing that people would oppose the company itself.
Yeah, so there are all these kind of cultural pieces in the way, but those, like a lot of things that we're seeing, like they sort of melt away in the use of it, So this idea of, again, like if you talk to my parents' generation and said, I'm going to just call up some random person and have them come pick me up in their car and take me to the airport, like that would have been insane. But Uber, Lyft, all those companies basically survive on that model because when like the culture can shift pretty quickly. And what's going to definitely drive automated vehicle stuff is um, it'll first be adopted by companies that just want to take human being, like like Amazon. How can they squeeze another 3 cents out of delivering a package? Well, trucking, it's like if if you drive on the freeway, trucks are pretty, like, unless something goes horribly wrong, like trucks are pretty, like, they don't do a lot. They just kind of drive along at a certain speed, follow another truck ahead of them, and the cars are zipping around all around them. And mostly what they have to do is like just try to accommodate the crazy humans that are around them. So I think when automated vehicles take that approach, they have to start from that perspective, which is safety is paramount, and exactly how that will play out. I mean, we'll start to see how that plays out as more and more of them come into and just freely driving in the world. But I think it will be driven by these commercial interests first, and then very quickly you'll have automated Uber, which is some other giant company which is absorbing all the risk. And it won't be individuals with, incredibly complicated or insurance policies. It'll just be like, Uber just figured out now they don't have to employ any people. And that's part of, one of the reasons for doing that. And it's something that we as engineers really have to consider, like, what is the role of human beings in this future society? And I love talking about that, but I probably shouldn't talk about that right now. Other comments or questions out there, and then we'll go in a little bit deeper on sort of the computery stuff. Okay. So I'm going to go ahead and close this slideshow, and I'm going to take a look at this codes and coding slideshow. So this is going to start with really some basic ideas of how information is stored and processed in the world. So, the big spoiler is basically information could be stored in different ways. And it was actually when I was at UC Davis moonlighting in the art department of all places where I started to learn about this subject called semiotics. And semiotics basically takes the idea of language and tries to break it down into some pieces. And it ends up with this triangle, and it has like these really abstract ideas of a symbol, a referent, and a thought or a reference. Now that's pretty abstract. So let's try to like bring this into the real world. So the idea is that, and this, by the way, is not a real cat. It's a picture of a cat. So I ended up having to use a symbol to symbolize something that, because I couldn't really get the real cat. But in this semiotics like idea, there is a real cat somewhere in the world. And then we have different ways of sort of communicating around that. So inside my head, I have this thought about a cat. And we're starting to piece together how the mind, like, how that stores that, how it like what that symbol, how it's articulated. But mostly, like, if we go out into the real world, the physical world, right, we can have a vocalized sound, cat, right? There's that waveform cat that computers now can distinguish cat from bat, from hat, right? And they're just that slight different change in consonant at the start. So there's that kind of way of triggering a human being to think about the cat. And it can be in different languages. So we have, like cat or gato. We have symbolic pictures like this little symbol of a cat, which is not representative really of any specific cat in the world, but is a generalized symbol for a cat. Does anybody who speaks more than one language and they have kind of that abstract idea of a cat, do they have a different image that comes to mind when you think of cat or dog in the different cultural kind of manifestations of language? So sometimes you'll find that that's true. So in certain environments and cultures, for example, dogs are a much more kind of fearsome animal than they are in the United States, because a lot of dogs roam wild. There'll be packs of dogs in the street. When I worked in industry, we had a an engineering center in this little village. It was like a town in Romania. And one of our engineers was out wandering at night, like taking a walk, and got attacked by some dogs. So like in different cultures, sometimes there's different associations with these words and these ideas. And so like it might point to something subtly different in your head. And so we all have a very sophisticated kind of way of working with symbols and working with kind of their representation of what they mean in our head, and then sort of this externalized things of what they really are. So code in general is a system of these signals, and this is dictionary definitions, used to represent letters or numbers in transmitting messages, right? So a system of signals could be just like the waveforms of my voice, right? We're really going through that, using the audio channel to transmit ideas right now. Code also has this kind of secondary meaning, which is like hiding things or finding way to express a complex idea or thought in a very brief way. Morse code, which most people have heard, like kind of like what it sounds like. It's like beep, 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 beep. And for anyone that knows Morse code, I apologize. I don't know what I said. It could have been really rude, inappropriate, or whatever, but it's just because I'm ignorant. I didn't intend to say anything. But of course, the idea of the Morse code is the two symbols are the dot and the dash, right? So it shares a lot with our current computer thoughts of things being either ones or zeros, right? So in the abstract world of the computer, we have ones and zeros. Everything's ones and zeros. It's binary. It's a binary code. Well, binary codes existed long before the computer kind of took over and became an example of it. So this is an example of the way humans used a binary code to transmit messages. So again, like we have to kind of like take a moment and visualize being back 150 years, maybe 200 years ago, and think like, how did I send a message to someone in Watsonville? What were my tools?
Smoke
I had my,
signals.
wait, go ahead.
Smoke signals.
Yeah, you could, like, there was ideas of smoke signals. So if there was actual enough visibility between the two locations, you could use smoke as a signal. Of course, the other side has to know what they're looking for. But oftentimes, if I wrote a letter, I had to somehow get it there. So physically, you'd either walk or you'd have, like the Pony Express is kind of this thing where it was like, no, we have a whole system. You grab all the letters and you get on your horse and you're like, ah, well, this was replaced by this idea of a telegraph. And the telegraph, uh-oh, I just gestured wildly at my keyboard, and let me catch up again. Somehow it opened Outlook. Go figure. Let's go back to here. One sec, sorry about that. My wild teaching style. So that, I have a light switch on the wall right over there. I guess you can, there it is. It's right there. So I flip that switch on, right? And the light above me goes on. And there's an electrical circuit that's made. And so the electrons basically can flow through the switch, through the light bulb, back through the wall, through the electrical system, back all the way out of my house, like down the street, through the electrical poles, like all the way to some generation station or someone that's providing those electrons for me. Well, the idea of Morse code was essentially like, what if I put a light switch? It didn't use light, but it used a little like clicky thing. And I just constantly turn it on and off. So I go tap, 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 tap here. And then on the other side, something goes click, 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 click. And so you just had two human beings on the opposite side of this long wire loop, and you could communicate. So that was an early electrical engineering feat. Here you see the telegraph key, and here you see the sounder. So you would close the circuit in one place, and somewhere far away, the circuit now being closed would cause this little clicker to click. And someone was there just taking notes. Oh, I heard, oh, okay. Oh, that's too bad. Someone passed away. And, you're kind of like taking the note. And then you take your copy that you made of the message and you bring it to the person. So that was like an early tech job. You could be the telegraph operator in each of these towns, and you would, communicate messages. They would go through this system and get passed from telegraph operator to telegraph operator. And you could communicate all the way across the country by just this kind of like tapping code. And again, that was all based on a binary code. Let's go back to it just for a second, because I do want to emphasize one thing. This code was designed because human beings are inherently sort of lazy. And I don't mean lazy in a negative sense. I mean lazy like, why would I do a bunch of extra work if I don't have to? So you'll see that symbols that are used often, like E, I, N, M, they only require like one or two symbols. There's others that, that are not used very often, like Q requires 4, Y requires 4, X requires 4. So they basically decided the code based on how often it's used. Does anyone know how this keyboard got laid out like this? Like why it's laid out in that particular way?
I seem to remember it was there was a gosh, I actually just read about this in my typing class, but it has to do with again the frequency of numbers used in a sentence, right, or any given statement.
Yeah, so the old typewriters, the way they worked is they were like a physical lever. You'd push down on this little hammer would go up and hit the paper, and they would come from different places. And so the way it's laid out is so that typically there would be an alternation in most letters from one side to the other so that the hammers wouldn't collide. And so it was built around that process. And so that's why we have the QWERTY keyboard, is because it has to do with like the frequency of usage in common language. And it came out as sort of an engineering decision that this keyboard layout makes a lot of sense. I kind of accept it, like I took typing class and I learned that touch typing, I could do it all like without looking at the keyboard. But it's funny to realize that someone just a long time ago made this decision because, oh, damn, the stupid typewriter keeps getting tangled up. Let me change the layout of the keys. Okay, so let's go forward a few steps. We have other binary coding schemes like Braille. So Braille is this 6-dot system. And the idea is that for someone that has a sight impairment, they can feel these 6 dots and they can recognize the different patterns. So this is, again, a binary code. There is either like a little bump or there is no bump. And so in this system of binary codes, you have 2 to the power of number of digits. So this has 6 possible digits, 6 possible bumps, ones and zeros, if you will. And it ends up that this can carry 64 different symbols. So that's enough for the alphabet, letters, and numbers and things, punctuation. So when you go through and try to learn to read it, you have to get, you have to detect those individual bumps. Now, this is just like that little breathing exercise at the start. It's hard to imagine as a sighted person that you would be capable of doing it. But if you spend a little time just trying it, you'll find that no, actually, I can tune my neurons, my sensory system to really feel the difference between each of these different letters, and then bypass the whole thought process to automatically process it into like sweeping across and reading it in the same way that, I don't look at it. I don't look at this title and say, okay, that's a T, that's a R, an A, an N. Okay, that's Tran, okay. And then S, and then, like, it's chunking it. So your brain has this capacity of chunking things. And so it's just amazing our capacity to basically store and learn different systems of getting information.
Carl, I
Um,
once watched this documentary where they intentionally blindfolded people that had true sight
yeah,
for a month, and every day they had a little tiny thing that clicked their fingertip. Just a little tiny, like not electrode, but a mechanical, almost like a needle, but not with a point
yeah,
on it. And it tapped their finger. And at the beginning, when they were with their sight, they tried it with their sight, and they were not able to detect like how many times it hit their finger and how fast, and the frequency and the spaces between. But within a month, they were able to to detect it as almost as well as a blind person, because the visual cortex essentially shut down and decreased its activity, because they were also doing the EEG at the same time, and while there are other parts of the brain that's for sensory touch and stuff heightened.
yeah. I mean, the brain is like remarkably resilient. My mother-in-law had a stroke recently. There's different kinds of strokes, but it was a kind that you have a bleed.
Sorry to hear that.
Yeah, it was a bummer, but the kind of amazing part is that, you go through this, like your brain, that part of your brain just starts to not work. So something else takes over. And it's really interesting. She was a native German speaker. So her language is a little bit more like blended together, but there's the human brain is just amazingly resilient. And that's why those learning algorithms are so interesting, because they don't rely on this like micromanaged old school programming style. They basically look at patterns and see those patterns. And when the patterns change, it'll just automatically respond to it. So like the facial recognition stuff of these phones that looks at your face, it's not wrapped up in whether you have glasses on or facial hair. It's not using that kind of approach. It's a whole other approach. And the mathematics of how that works is shockingly like deep and cool and amazing, actually. And I'm all
Or
like,
how they
oh,
even
I
had
want
to
to.
compute the for the facial recognition for when people were wearing masks.
Yeah.
So that was interesting. I was learning about that. It was wow.
Okay, so Braille is another kind of binary code. These codes, these universal product codes, they're also binary. There's like a thick line and a thin line, and that turns into ones and zeros, and then that can be translated into decimal values. And so returning back to this idea that information could be stored in various ways, like we're already seeing these examples. We have in our own experience different examples, the kind of verbal language, the written language, even gestural language. No matter who you are, there's certain hand gestures that you would recognize and associate with certain feelings. It turns out we can also encode instructions in the same kind of systems. So the kind of natural evolution as we went, what really took out the telegraph? Does anybody know what took out the telegraph? The telephone. why pay someone to translate your letter into like these little dots and dashes when I can just pick up the phone and call Aunt Mary? Hey, Aunt Mary, there's no translation required. It like directly goes through the technology. The vibration of that little microphone here turns into the vibration of a speaker, just like this is working right now. And you don't have the intermediary. But we got to this point where we still needed to send documents to one another. And to avoid basically taking a typed document like a contract and putting it in an envelope and then sending it to some other place, they invented this notion of a teletype machine. And a teletype machine is essentially kind of like a telegraph where I can type on one side and it comes out on a typewriter in some other place. And it used the phone system to do that. So how do you think it sent binary information over the phone?
Through different tones.
Different tones, you know, just as simple as like a low tone as a 0 and a higher tone like as a 1. And so it would send binary information. And so if you've ever heard like an old modem in an old TV show or something where they're connecting to the internet and they're dialed up the phone, it's going like bong, bong, beep, like that. Those are the sounds of the ones and zeros that they're communicating back and forth. And so the thing about a typewriter is that there's more than just data that you sent. There's like behavior. In other words, when you get to the end of the line, you have to go back to the start of the line. And sometimes you want to end a line halfway through because you finished your sentence and you're on to the next paragraph. So you have to do things like go to the next line, indent, you know, back up, overtype, like strike over. And so these first, you can see in these there's 7 columns here. Actually, there's 8 columns. There's yeah, there's 8 columns there. No excuses to be made. But the first 2 are controls. So they are sending signals, and the first one is a 0, 0, 0, and it just means nothing. Don't do anything. This one, LF, line feed, that means go to the next line. So there are all these ways that you can now start to send controls to these machines on the other side, and it would take on behavior. The reason I bring this up is because this is sort of the natural evolution of how modern programming and how modern computers work. They break the information that's stored on the computer into 2 different things. There's like the data, the like information about the system or the program, and then there's the behaviors of the program. So to talk about this, I want to jump out to this game, Pong. Let's play. I played hard earlier and it was really hard, so I'm going to play medium. Oh man, it's not giving me is it automatically keyboard controlled? Wait, how do I get to choose my controls? Let's try again. No, I guess I just don't get to. I did this on my, here, let's try this. Maybe the Edge browser will work better. It's funny, I tried this on my Mac and it worked just fine. But of course, let's see if I can grab this and bring it down. All right, first let's get rid of this. Then let's grab this. Really? Do you work with the keyboard? No, how come I can't control my controls? All right, Flash game isn't gonna work. Anyway, you've probably seen this game. You have this paddle and it moves up and you try to knock the ball back to the other side, right? So let's, rather than obsess about my inability to play this, let me try this, main menu. No, it's just not asking me how I get to control it. As we watch that, let's try to think about the things that are the state of the game versus the behavior. And to do that, I'm going to bring this little kind of virtual whiteboard. And let's think about things like in terms of the data and then the behavior. So how would I how would I think about, or how would I keep notes about the location of the ball? What do you think I would need? What would I need to track for that?
Like a graph system?
Yeah, so I'd need like
Latitude
a,
and longitude,
yeah, like X
or
and
like
Y,
X and Y, yes.
latitude and longitude. Like you need some position information, right? So I stored two pieces of data, the X position and the Y position, the latitude, the longitude, any of those, but I need two pieces of data because it's in a two-dimensional space. So that's like something I would store. I might also store something like the score, right? I have to keep track of the score. I have to keep track of the paddle position. Apparently I can't spell at all. And this would basically be the height, because I can't move my paddle this way. And there'd be one for the left player and height for the right player. There's also the velocity of the ball. What are some behaviors I would need to track? Like the ball hitting the paddle.
Scoring. A goal, actually, passing through the goal zone.
Yep. So scoring,
And tracking the actual paddles.
tracking the
I guess
paddles.
you did that for data, yeah.
Well, because there's something we've kind of already glossed over. Computers use ones and zeros, right? It's all ones and zeros. How are those ones and zeros represented in a chip?
Off and on.
Off and
No,
on,
up, yes and no.
yes and no. But ultimately, that'll come down to either charge or to a voltage. So the
Gotcha.
idea is that an electrical engineer will think of a chip as like a bunch of voltages and currents and like all of the things associated with the electrical engineering description of the chip. The software engineer will look at that same chip and see, oh, it's doing calculations. It's ones and zeros. They're both right. Like, it isn't like one is right, more right than the other. It's like those two interpretations of the world are both correct. It's just that by thinking of it in ones and zeros, I can store things like all sorts of information, video, audio, programs, blah, 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 all the things that you've seen on a computer. But the electrical engineer is kind of like thinking of it as like, no, they're all voltages and electrons and currents and flow and transistors. And they enable, it's like that dance between the two enables that whole world. So of course we have to track the paddle, which is connected to a controller, and that controller is little like electronic switches or voltages, or somehow it's converting that. So that I would put in the behavior column. There's also things like the end of the game. There's like triggering sounds. And, lots of other things. But I just want to kind of distinguish between those two ideas. There's like the state, the information that, is like the model. It's like, what is the current state of the model? And then how that model evolves in time is really all this behavior. So when we take a look at slightly more complicated games, Oh, this was just the slide for building the model, but like, this is an old school Mario game. And, if you've played this game, you know that if Mario jumps up right now, he'll hit this brick and the brick will break. And that's behavior. It's like, it's learned to break. But these same pixels, like here, these little trees, I'm hoping you can see my cursor over here. He walks right past those, right? So it's not about like pixels or anything. It's really the underlying model of what is in the foreground, what is in the background, what are the behaviors. He's Fire Mario, or like he's just Big Mario, but if he gets the fire flower, he would be Fire Mario and he could shoot fireballs. And then, I think this is the Koopa. Is that the turtles? Koopas? Anyway, it could get flipped over and then it's just shell and you can kick the shell. There's all this stuff going on in this game. It's a little bit more complicated in Pong, but not incredibly complicated. Then you get into this. I thought this was, this is a little old, right? But Halo is one of those games that really has a lot of data. It's a lot of there's a lot of voiceovers, a lot of like acting that comes into that game. There's a whole storyline and everything. And then you have Minecraft, which is basically all behavior. It started from one programmer basically saying, let's make this game where everything is just like a block, and then the blocks can be combined into other blocks. And how do you share worlds in Minecraft? Do you remember how to do that? Has anyone done that?
As a file?
There's these little seeds, right? These little numerical codes that if you give to someone else, it'll create the whole identical world. And so that seed, like if you think about that, it's like a starting point, and then it does a calculation on that number, and that leads to the entire creation of the world, which is kind of an interesting idea. And it comes down to how computers do fake randomness. Like computers use pseudo-random stuff instead of true random. Anyway, weird aside, but the idea is that with that single seed, you can reproduce the whole Minecraft world, which shows how it to me, that indicates how much it is about behavior and about processing. So I can give you this simple number, it'll compute, and it comes up with the same world. Whereas in Halo, that's all pre-decided by like producers and actors and programmers and all these people that work together to produce that game. Not a big deal, just something to note. So we're going to do a little project today. It's called the Hour of Code. And there's some basic basic structures of programming that I think we want to touch on first. So I'm going to go ahead and play this. Oops, it just went to the next slide. Let's try this again. There we go.
Okay, now you're going to press run.
Actually, I already missed it. Let's go back to this one. This is the one I really wanted to play.
Behind all of the software that we use on a daily basis, there's a code being run with all sorts of different terms and symbols. Surprisingly, it can often be broken down into 3 simple programming structures called sequences, selections, and loops. These come together to form the most basic instructions and algorithms for all sorts of software. A sequence is a series of actions that are completed in a specific order. Action 1 is performed, then action 2, then 3, etc. until all of the actions in the sequence have been carried out. A sequence we do every day is a morning routine. You might wake up, drink some water, take a shower, eat breakfast, and so on. Everyone's routine is different, but they're all made up of a sequence of various actions. Selections are a bit different. Instead of following a specific order of events, they ask a question in order to figure out which path to take next. Let's say you go to brush your teeth and you find that you're out of toothpaste. You'd then ask, do I have any more toothpaste? If the answer is no, then you would add it to your shopping list. But if the answer is yes, then you would just use the toothpaste. This is really all a selection is doing, answering a question based on what it finds. The third programming structure is a loop. Like selections, loops also ask questions. However, the difference is they ask the same question over and over and over again until a certain task is complete. For example, take the act of hammering a nail. Even though you may not realize it, you're constantly asking yourself, is the nail all the way in? When the answer is no, you hammer the nail again. You continue to repeat this question until the answer is yes, and then you stop. Loops allow programmers to efficiently code repetitive tasks instead of having to write the same actions over and over again. These three programming structures may seem fairly simple on their own, but when combined, they can create some pretty complex software.
GCF Global, creating opportunities for a better.
So those simple programming structures, when you do the hour of code, you'll probably recognize them used in different projects. So depending on which project you choose, you may or may not see all of them. But just keep that in mind, that there's really like this idea that you just follow a bunch of steps in order. And that the order is important, right? It's kind of like, well, I'm not going to go off on recipes, but you know, when you're cooking in the kitchen, it matters like the order in which you do things. You usually like there's a very specific order, and if you do it out of order, your food won't turn out quite the way it would otherwise. That idea of asking questions and making decisions, you know, so like even in those start screens of the game where it's like, do you want to play easy, medium, or hard? There's consequences to making those choices. And the computer sits there and waits for you to make a decision. It's making a loop. Did they choose yet? No. Okay, keep waiting. Did they choose yet? No. Did they choose yet? No. And so eventually they choose, the user chooses, and then the game kind of goes on from there. So you'll see as you start to think about those kind of those three methods, those three structures, you'll see them kind of playing out in the programs that you work with every day. So the next thing we're going to do is this. This is just another video. It's about the hour of code. And we'll watch that, and then I'll get you started.
This is so cool.
Hour of Code.
The Hour of Code. Todos lo pueden hacer.
Ya programmi ako. Man, shahilo do khat kod.
Your teacher says you guys are into it.
We are. It's very awesome.
Students around the world had an hour of code today. It's part of a global movement to show kids what it takes to create the programs and apps they spend so much time using.
The largest education events in history.
Organizers set what they called an ambitious goal of reaching 10 million students this week. Almost 15 million signed up.
This week, I'm proud to join the students, teachers, businesses, and nonprofit organizations taking new steps to support computer science in America's schools.
You guys are already getting a head start on taking over the world.
I got it.
They've been so excited about it.
They don't even have to be a computer science engineer. Maybe they want to do something else. But in our world, this is going to be the basis for everything that we do.
Move. Semicolon.
Look what I did.
It's so beautiful.
When you're building a program, you have to think outside of the box.
If you can change technology, you can change the world.
I challenge girls in every single country to learn 1 hour of code.
Every district should do, every district can do it.
Please help us get the hour of code to every school and every classroom and every child.
And my school's doing it.
So the hour of code idea, right? It's really recognizing that shift in the world. And so as a person that kind of lived through that transition where computers were this thing that were like an entertainment, you played games with it. And then I went to college and I started to study engineering, and I saw how calculus and traditional mathematics solved certain kinds of problems, but really was incapable of solving other types of problems. The computer and the idea of coding and these repetitive processes and the asking of questions and then getting answers and then evolving that, taking it all the way out to where we are now with neural networks, with special chips to do neural network type programming, to do pattern recognition, to use machine learning, and to use artificial intelligence, all of those pieces fitting together. The concepts of coding, it becomes really important for everyone, I think, to have some sort of access to that type of thinking. And I don't want to become complacent with that idea that it is a different kind of thinking. It really, like when I went to college, I had a different kind of way of thinking about problems than other people, because other people thought a mathematical description that covers all future and past states was like that was the ethos of engineering at the time. And it slowly transitioned into this thing where I don't really have to know that far ahead in time. A quadcopter only knows it has to know what its goal is for the next millisecond. And the next millisecond is to stay level or move it forward a little bit. And so that will definitely kind of play into almost everyone's engineering career, no matter what type of engineering, even civil engineering, because the manufacturing and the construction processes will involve these tools. So in any case, the goal is just to go through and do this project. I'm going to break people out into breakout rooms. You can pick one of several different projects. I'm going to bring up the website again. Oh, actually, I just have to escape out of this. There we go. So if we go back to the module, there's a project down here called Project Week 8, Hour of Code. And so the goal is to pick one of these projects, and I broke it down into these. I looked at all of them. I went through all of them because I wanted to make sure that they were one, that they ran in a browser, right? There's Hour of Code stuff where you have to download stuff. And I wanted to make sure that they would run in a web browser. I wanted to make sure that they had the basic elements of it and that they were kind of a wide variety of things. So there's like a kind of artist inspired one. There's kind of a Guitar Hero kind of react to things like a rhythm game, like react to inputs from the keyboard. There's like App Lab, which is kind of mimicking the way you build an iPhone app or something where you have little buttons that you push. There's a RoboBlocky, which is taking those structures and they make little blocks, and then you have the robot perform these functions to do these work. There's a music making game, kind of a beat making game, and then a sports game. So if you have some computer experience, you have some programming experience, you can pick a different one in this giant list of them, but just be aware that some of them would require downloading software, or will require installing software or writing code. So these were all like, I picked them because I knew that everyone that can be on this Zoom with me would be able to make one of these work. So while you're working through that tutorial, just learn through some of the processes to think through what's happening, kind of reflect on it, which I just want to know which one you did, what kind of got in the way, what did you learn along the way? Usually what happens is you have an obstacle, you have a challenge, and that's where you devote your effort to trying to get past that obstacle. And then really seriously think if you have other siblings or younger siblings or other kids in your family or kids in your environment, to teach them these things, because it'll be really valuable for them to learn these basic skills. And what can you share from what you're learning in this class with other people? And a lot of times the tutorial will give you a URL, like a web link that you can then give to me, and I can go see your project. So I could see like what beats you made, or like what your art thing was. And so basically your grade is based 50% on like participating and doing it, and then 50% on answering those questions. And I'm going to encourage you to work with the other people in your breakout room so that you can talk through questions, share screen if you get stuck. But I will kind of start one of them so you can see kind of the process. So I chose, I'm going to skip this. It's just a really short introduction. And usually the way it's broken up is there is a little video. So it's like a minute long. I'm going to go ahead and watch
Hello,
that.
welcome to the Peblio Hour of Code tutorial. My name is Dan, and I'm here to teach you the very basics of programming. You're going to learn to write your first computer code in the language JavaScript with something called P5. So the exercise, the activity here is to make a piece of art, a composition. And on the Peblio page, you can look for some inspiration. So you can click through these slides and see famous kind of geometric art by artists throughout history, and look at these and try to think of what you might want to make your own design just with shapes and color. Get out some pencil, get out some paper, get out some markers. Try doing it by hand first. After you've kind of gotten your idea, in the next video, I'm going to show you what is the syntax, how do you write lines of code, and how do you draw shapes to a computer canvas. At the end, I'm going to show you a little bit about making it interactive and animated, and then a way that you'll be able to share it with your friends and family and anybody else that you want to share your composition with. Okay, are you ready to get started? You're about to write some code. Take a minute to look through, get inspired by the art, and then I'll be right back to show you more about writing code.
So it's all broken up into these little bite-sized lessons. And so as I scroll down here, you can see here's the, the slideshow of different artists, Alexander Calder, Mary Kors, Olafur Eliasson, Dan Flavin. So you can kind of get an idea of just, and of course you can try to mimic one of these artists, or you can kind of go off on your own. But the goal in this is to kind of slowly build from tiny little pieces into more and more complexity. So this next video talks a little bit about how you
One thing that I want to quickly mention when you get started.
The code editor. I started a little soon. And you'll talk about that.
Writing the code is I'm using a different code editor than what you see on the Peblio page. The code editor I'm using is something you could use later. It's at editor.p5js.org, but you have a code editor right here in the Peblio page. So as I type code, you can type the same code in your editor, and what you'll want to make sure you do is go and click this play button to run your code. Any error messages will show up down here in the console, and you'll see something similar happen as I code as well.
So just another kind of leading you through the process. Here's another video. It's about 2 minutes, and it talks about the basic parts of the code. In this case, I'll probably watch this one, and then we'll run it, and then I'll let you guys work. I just want you to kind of see the process. So if you're kind of feeling like you got orphaned, somehow you got separated from the tutorial, because all of these should have a tutorial that helps walk you through it.
Hello, it's time to write some code. So what I have over here is a code editor. This is the P5 web editor. It's an editor that you can use after you finish this Hour of Code tutorial, but if you're in the Peblio site, your code editor will look a little bit different. But ultimately, here's the code, and here's the result of that code. So the first thing that I want to explain to you, and I'm going to come over here to this whiteboard, is what are the elements of a line of code? Now, lines of code can be lots of different things, but the core element that you're going to start with is this idea of a command. A command, another term for this, is actually going to be later revealed to be called a function. You're calling a function. That command is going to be an English word followed by an open parentheses, a close parentheses, and some number of what are called arguments. So the arguments are the things that modify the command. And then the very end, a semicolon. The semicolon is telling the computer, I've finished my instruction. This is a single instruction, what I want to do, and things that modify what I want to do. And we can see two examples of that here. I want to create canvas, and I want the canvas to be 400 pixels wide and 300 pixels high. And then I want to draw a background, and I want the background to be some color. Later, I'll get into exactly what 220, 0, 200 mean, but ultimately, those are numbers that indicate that I want the background of the canvas to have this pink color. So you can now scroll down and look, and you're going to find exactly this code in the Peblio tutorial. The first thing you might want to try is just change those numbers, 400 and 300. Try to get a different size for the canvas. How does that look? Pick your favorite size. You can also try messing around with these numbers, 220, 0, 200, and you might see the color change. But again, we'll get into the specifics of that later.
So the idea is that here I have my little editor. So for example, I have create canvas, the background here. I click the run code, and I'll see over here that it popped up, right? So I'm gonna expand this so I have a bigger editor. So let's say that I don't really know what these things are. I'm just kind of playing with it. What if I did 40 by 300? Please stop helping me. All right. Copy to your account. Just browsing. Oh, probably wanted to say don't ask me again. So you can see it's not as wide. So the first number is really the width. So if I wanted it to be wider, I could choose 600 or something like that. So that idea that I have a command, it's doing something, it's creating the canvas, and then I'm modifying that command to give it very specific instructions. I'm telling it to make it 600 by 300. This color thing, this is an RGB, red, green, blue number. So if I wanted to find out how to do, I might look up like web colors. Yeah, let's do web color chart. So if I wanted to pick like, oh, this kind of orange brown, you can see that it gives me a couple of different options. And the one I want is the 212, 172, 13, right? So it told me how to pick that. Let's say I want to do, yeah, let's do that color. So 212, 172, 13. I go back to my hour of code thing, which is here. No, that's the wrong one. Here it is. 212, I already forgot what it was. I had too many steps. 172.13. So I run this again, and you can see I can change the color. So I'm taking a command and I'm modifying the command to do my bidding. And this is what really attracted me to programming, is this idea that I have so much control over its behavior. So at this point, I'm going to let you guys play. I'm going to send you off into breakout rooms. You know, if you have questions, first ask the people in your breakout room. Reach out to me in the main room. If you need to have a break, and normally you will have a break, so feel free to take the next 10 minutes and walk away, and then come back in 10 minutes or something. The hour of code is not timed. It's like the process is like, it might take you 2 hours because you're playing a lot and you're trying a lot of things. It might take you less time, but the idea is just to get through the basic principles of programming and explore them. The assignment isn't due at 2 o'clock. It is due at the end of spring break on that Monday. So if you end up not kind of hitting the timeline, feel free to continue at your own pace. Just make sure you submit the assignment before the due date. And I'm happy to ask any questions. And they could be about this project, or they could be about any of the other stuff we talked about. So I'll leave that as an opportunity. And otherwise, I'll put people out into breakout rooms. Does that sound good? Feel like you know what to do? All right, cool. All right, let's see. Where's my breakout room tool? Here it is, breakout rooms. So this will break people into like groups of 3 or 4. And like I said, just introduce yourself to the other people in your room, say hi. You guys will probably be spending a lot of time together in the next couple of years. And, oh, you know, I'm gonna stop the recording now and then we'll break out.